Hello and welcome. Today we're going to have some fun. In William Barton Jr.'s book, Color Computer Graphics, there's some cool code to show us how to redirect the video display generator to show any page of memory, not just a page that's dedicated to showing output. The problem with the code, though, is the screen snaps back to the way it usually is once it's time to go back to start typing or doing anything in the basic interpreter. So today, we're going to hack the ROM so that it makes the VDG do what we want it to do, rather than snapping it back to do what it wants it to do. That sounds like fun, doesn't it? Let's do that. Also included on today's video, debugger watch points. Me confusing the line buffer with the string buffer. ROM to RAM. This introduction. The video display generator in your Coco is capable of displaying any page of memory on your screen. So what we have here is a diagram of memory that continues and continues and continues, starting at 0. And it's divided up into pages of size hex 200. So the 0th page goes from 0 to 1FF, the page after that goes from 200 to 3FF, and so on. Now by default, this is the page that's shown when the text screen is active. So that's from 400 to 5FF. So that's what you get when you boot up, when you're typing on the screen. This is the page that you see. These are the locations in memory that all of that stuff is stored. And that's what the VDG is going to show. The way the ROM gets the VDG to show it is by poking a series of bytes in a series of addresses to tell it that this is the page that you want. If you look at these purple binary numbers, you'll see that they go up by 1 for each page. And that's the identifier of the page to show. So let's say this is the one that we want to show. We have to make sure that this purple value is the one that gets poked into the VDG. The way that's done is by picking addresses here that the VDG listens to and poking at the correct address. So if I want a 0 in this spot, I have to poke into FFC 6. If I want a 1 in this spot, I have to poke into FFC 9. And so on, FFCA, FFCC, FFCE, FFD0, FFD2. The interesting thing is it does not matter what value you poke. You can poke anything you like. All the VDG listens to is where the poke happens. That's why there are separate addresses, whether you want a 0 there or a 1 there. What we'd like to do is to change that. So for example, an interesting thing you could do is to take a look at what the internals of BASIC are doing when you run code, when you type on the screen. And if that's what you want a 0 in each of these spots. And so you would poke into each of these even numbered addresses. Another thing you could do is look at other basic internals, which would be on this page, and in that case, these are the addresses that you would poke to get that page to be shown. In the book, the Color Computer Graphics book, they have code to do this, so that's what we're going to try first. We're just going to poke these addresses and take a look at what that shows us. This is the code we're going to run. This was taken straight from the book. It's just poking into all the even numbered addresses, and the 0 here doesn't matter, you can poke anything. But that's all that we're doing. And then at the end, we just hang on so we can see what's happening. So let's run it. So this is what BASIC looks like while you're doing a 140 go to 140, which is that line that we're executing right now. And some interesting things happen if you start typing on the screen, on the keyboard. So if you keep your eyes over here, as I type different keys on the keyboard, different bytes get written into those areas of memory. No one is doing anything with them, but they're ready. I don't have a keyboard joystick set up, but I presume if I did stuff on the joystick, maybe you might see some stuff here. And then you got some like crazy things zigging around, doing whatever they're doing. Who knows? But what I want to do is take a look at that string buffer. So the string buffer is actually going to be in the next page because the string buffer starts at 03D7. So we want to take a look at what's going on at 03D7. So that's going to be the next page, which means we want to make sure that we're poking FFC7, but all the rest need to be zeros. So all the even ones, except we're going to do an FFC7. So here, instead of the FFC6, we're doing an FFC7. And here we go. We're now looking at the string buffer and some other random stuff. Looks like maybe this is the string buffer. This might have been the last thing I did. If I start typing, nothing really happens. In fact, all we're doing is we're still just executing that 140 go to 140. So not much is going on. What would be cool is if I could get to see what's happening while I'm doing stuff, while I'm running a real program, while I'm typing into the basic interpreter. But the problem is that as soon as I break out of the program, Color Basic takes control again and it says, ooh, who screwed around with the VDG? And it like sets it back to the way it likes. I would like to be able to break out of the program and for it not to do that. I want to keep on viewing that. So one might wonder, where in memory is the ROM that is telling the VDG to go back to a thing I didn't want it to go to? And we can figure that out in a couple ways, but I think maybe the most fun way is to use the debugger and set a watch point. So what I'm going to do is I'm going to set a watch point on FFC6. And I'm going to find out where are the places in the ROM that keep changing FFC6 to stuff. So I started up main with the debugger, and I'm going to set a watch point on FFC6. I'm only going to make it 1 byte long. In theory, I could do a watch point over that whole region of memory, but then I'm going to keep hitting the watch point every single time any one of them is poked. I really only care about one of them, so I'm just going to pick FFC6, and then W means write. So we hit it fairly early, right here at A056. Keep going. And then again at 95BF. Keep going. 9F5BF again. 95BF again. 95BF again. 95BF again. Oh goodness. So it looks like this area is called a lot. Okay, now we seem to have stopped doing that, which is nice. Okay, so now we're running. So I'm going to run my program. As soon as I hit a key, 95BF again. Okay, run. Sorry, run. And we've hit it again. So I'm pretty sure that 95BF is going to be a location I definitely need to change. That first one might not even matter because it looks like whatever's going on here is overwriting it or overriding it. So let's take a look at what that stuff is doing. If we look in the extended basic Unravelled book, 95BF is listed, and it's part of a set of code that they call Setup the SAM and VDG to Graphics Mode. So it looks like this is code that's run frequently, almost all the time, to set things up the way it needs to be set up. And this is the line of code that ends up deciding that that memory address is going to get poked to. So let's take a closer look in the debugger. So the value of X is FFC8. And since we set our watch point on FFC6, it would make sense that actually this is the line that was causing the change, because X minus 2 would be the address for the watch point that we set up. So this is the line that seems to be undoing the work that we're trying to keep persistent. So what we could do is start poking into this memory and change the ROM so that it'll poke the things that we want to poke. In fact, if we do that, we don't even need our program anymore. We don't even need to run that series of pokes from before. We just change the ROM directly, and then the ROM will do our bidding for us. And then it'll not only be instant, but it'll be persistent. So let's do a little thinking. What exactly are the changes we would need to make to this ROM? As a reminder, we want to poke C7, and we want to poke C8. And right now we're getting the reverse. We want a 0, 1 there, and right now the ROM is doing a 1, 0. So we want a C7 and a C8. Since the X register is sitting at C8, these are the two lines currently in the ROM that we want to change. So this is subtracting 2, so this is adding the C6 poke. This is adding 1, so that gives us the C9 poke. Since what we need is C7 and C8, we could make these changes to get it. So add nothing to X because it's already right where we want it, and then just subtract 1 to get the C7. That means these are the bytes that need to change. So sitting at 95BB is this. At 95BC, we want to change that to be 00, 0, and at 95BD, we want to change it to 1F. So let's give that a try. Let's just start here. Let's poke 95BC to be 0. First, let's just make sure things are what we expect. Oops, peek. 95BB should be A7. Good. And the very next one. Is at 1, which makes sense. That's the current value. So we're going to change that second one to be 0. There we go. And you notice nothing on the screen changed. Let's make sure our poke did anything. No, our poke did nothing, and of course it did nothing because this is ROM, folks. You can't poke ROM. What kind of crazy person thinks he can poke ROM? Someone who has a ROM to RAM utility thinks he can poke into ROM. That's who. Alan Huffman's blog has a few posts that talk about this. In this post, he even provides a very nice basic listing of some code that will, if you have, say, a Coco 2 with 64K of RAM, which is what I have, it will switch to using that hidden 32K. So in order to get 64K, you got 32 you can address and 32 that's kind of like hidden, that only assembly language can access. So it'll flip that into the foreground and it will copy all of the ROM into that high area of RAM. So really the same addresses that the Coco expects the ROM to live in, it will now have the ROM still, but it will be in RAM. So I should say the ROM routines that it expects to be at those addresses will be still there, but those addresses will now refer to RAM. All you got to do is type this in and run it. For those who are interested, there are other blog entries on his same blog that talk about the history of this utility and where it first appeared. I've seen it in Rainbow, although it seemed like it was written slightly differently. There are a couple sources that predate what I had found. So it's kind of interesting reading if you're curious where this came from. So here's what I took from Alan's blog. And one of the things that this does, by the way, to prove that it worked after it executes the code to do that shifty stuff, is it changes the OK prompt to be OI, which is a little bit funny and very much clearer, because then you know exactly how it works. So that's what we're going to run. There's my OI. Look at that. It's nothing is okay anymore. It's all OI. All right. So now maybe I should be able to poke with impunity. So let's try out that first poke. Oh, something has definitely happened. Look at that. Instantaneous and persistent, just like I promised. I haven't even done my second poke yet. So right now I'm looking at the 0th page, the one all the way at the lowest numbers of memory. We can still see what's in the text buffer though by using the memory window. So let's pop that up. All right, so if you look here, you'll see kind of a live view of the memory, which is really cool, by the way. You don't even have to stop at a breakpoint for the MAME debugger to update this. So this is showing us a live view. In fact, if I start typing, let's say, print hello, oops, I'm typing in the wrong field there. I need to type on the screen. Print hello. You can see things changing right here. Enter. And then it goes ahead and prints that, and you can even see it like scrolled up, which is kind of cool. All right, so I can do my second poke. What's that second poke? Now I want to go into BE and poke in a 1F. Poke 95BE 1F. You'll notice numbers don't quite show up like you would expect, but there we are. Now I'm in the other part of RAM that should be showing my string buffer. So I wonder what kinds of things I can do. So I'm going to start typing, and you can see I'm typing here. I'm going to type the alphabet, and you can see the string buffer is starting to fill up with the alphabet too. By the way, backspace also backspaces through the buffer. It's interesting. Boom, boom, boom. Yep, interesting. I'm just going to do a bunch of characters here. So those captions that were taunting me were letting me know that I was getting confused and I was looking at the line buffer, not the string buffer. So the string buffer is going to be starting in around this area here, not the line buffer, which is the buffer that BASIC uses as you're typing something. So here's some code that should make use of the string buffer, because one of the main purposes is in conversions from floating point to strings. So I'm just going to have a simple for loop that goes through some numbers. We'll convert it to a string, and that's it. It's not even going to print it. So there's my run showing up in the line buffer, not the string buffer. Keep your eyes down here. And there we go. So it's cycling through numbers from -10 to 10. By the way, I didn't have to make it actually be decimal numbers, even if they were straight integers. It's still using the same code to do the conversion into a string, so you would still see the numbers here. Okay, so I have finally seen the string buffer in action. Cool. Mission accomplished.